Okay, so we're going to extend related rates to a cone, which a cone is a little bit different because we have multiple variables working together here. So we need to make sure that we understand one little concept about a cone that is very special. So let's go through this first example and then we'll kind of formalize it. So it says sand is piled into a right circular cone at a rate of 8 cubic feet per minute. So a rate of 8 cubic feet per minute. The radius of the cone is equal to the height. That's a very important feature here. And that's not going to be true in every single cone, but for this cone specifically, depending on how like wide or how narrow the cone is, we have to know what the relationship is between the radius and the height. So how fast is the height of the cone changing when the height is 5? So let's go through and write down what we know. 8 cubic feet per minute, that's going to be the rate that the volume is changing at. So dV dt. We know that the radius is equal to the height, so I'm going to say R equals H. How fast is the height changing? So I need to know dH dt is what I'm trying to find when the height is 5. Okay, so here's the tricky thing here. I could go through and I could go and find the derivative here, but I'd have to use product rule. Okay, so before we do that, because we don't know anything about dr dt or any of that kind of stuff, so we're going to actually do one quick little substitution here that'll make this so much easier. If I know R is equal to H, and I have to make sure I know what I'm looking for. I'm looking for dH dt. So that means that I want this equation, I need it to still have H's in it. So if R equals H, I'm going to go and I'm going to plug H in here. Okay. Now I could plug R into here, but we know that we need to find dH dt, so we want to keep H's in our formula. So if I make this V equals 1/3 pi H squared times H, I now have 1/3 pi H to the third. So that is technically, for this specific problem, that's going to be my volume formula. So now I can go and I can actually find my derivative. So dV dt is going to be equal to, let's see, 1/3 times 3 is just going to be 1 pi H squared dH dt. Okay. And now I can plug in everything that I know. So I know that the sand is being piled into the right circular cone at a rate of 8 cubic feet per minute. So I know that's going to be positive 8 feet cubed per minute equals pi. I know that my height is 5. And I know that I'm looking for dH dt. And that's going to be 5 feet. I didn't put that there. Okay. So that's going to give me, I'm going to go, actually I'll stay down here. 8 equals pi times 25 dH dt. So dH dt is going to be equal to 8 over 25 pi. And this is going to be, we have feet cubed divided by feet squared, so that's just going to be feet per minute. Now, when you go and put this into your calculator, if you want to get the decimal, you have to make sure that you put this in parentheses, because if you don't, your calculator doesn't compute it the right way. So when you put that into your calculator, I'm going to do 8 divided by 25, 8 divided by parenthesis 25 pi. And I get that dH dt is equal to 0.102 feet per minute. There you go. Okay. So what do we know? We know that the volume of a cone is always going to be equal to 1/3 pi R squared times the height. Okay. That's always going to be our formula for the volume of a cone. Now, if I have a cone like this, right, and I make a little triangle here, okay, and I have my height versus my diameter, okay, height versus diameter. So I know that the ratio of the, and this, we'll say this is our radius. I know that if this is a right triangle right here, I have a right triangle right, that as my triangle gets smaller and smaller and smaller, or bigger and bigger and bigger, I know that all of these things right here, this triangle, is going to be similar to this triangle, which is going to be similar to this triangle. So I know that these are all going to be similar triangles here. So I know that the ratio of the height to the radius is always going to be the same, okay? The ratio of height to radius will always be the same. So we have to remember that R over H is always going to equal whatever that is, A over B. It's always going to have the exact same ratio, no matter what, okay? So the radius and the height, and the height ratio will remain constant. Okay, so that takes away the need for both of those variables. We're just going to have to do a little bit of substitution as we go through our questions to either eliminate one of those variables. Know that in this question, sand is being poured at a rate of 2 meters cubed per second onto a conical pile of sand that is initially 2 meters in height with a base diameter of 6 meters. How fast is the height? So how fast, there's our question there. How fast is the height increasing? So that's going to be dH dt at the moment when the pile of sand is 4 meters in height. So we know that to begin with, we know that it's initially 2 meters in height. And I know that the base diameter is going to be 6 meters. Now, I know that the ratio of the radius to the height is going to be the same the whole time. So if radius to height here, my radius is actually only going to be 3 meters. So 3 meters to 2 meters, okay? And I know that V, I'm going to do this down here, V is 1/3 pi r squared times h. So we have to go through somehow and plug in. Now, if I want to know how fast is the height of the pile increasing, I know that I need this to be in terms of h, so I want to plug something in for r. So what I'm going to do actually is I'm going to do a simple little quick cross multiplication here, okay? And when I cross multiply, I'm going to get 2r equals 3h. So r equals 3h over 2, and that's what I'm going to plug in. Okay, now before we go and do anything with derivatives, I need to simplify this because this is an absolute mess and this is going to be hard to take the derivative of. I'm going to simplify. 3h squared over 2 is going to be 9h squared over 4 times h, which is then going to go to 1/3 pi 9h to the third over 4, which then I can multiply those fractions, and I get 9 over 12, which 9 over 12 is going to be 3 over 4 pi h to the third. Okay, so now I have my simplified formula. Now I can go and do my derivative. So dv dt is going to be, when I go and I multiply this, that's going to give me 9/4 pi h squared dh dt. And now I can go and plug in everything that I know. So I know that dv dt is going to be 2 meters cubed per second. I know that, now I know my initial height was 2, but I know that the specific point that I'm looking for, my height is going to be 4. Okay, that other height was just given to you so that you could find your ratio, but the specific point where we want the rate of change, the height's going to be 4. Okay, and then we just need to simplify there. So 4 squared is going to be 16. 16 times 9 over 4, that's going to give me 36 here. So 2 equals 36 pi dh dt, and then I can solve. So I can say dh dt equals 2 over 36 pi, and that's going to be meters per second. And then I'm actually going to simplify that. 2 divided by 36 pi is going to give me 0.018, always go to 3 decimal places, meters per second. Okay, so that's going to be the rate that it's changing at. Now let's actually finish this off and write a little sentence. When the pile is 4 meters high in height, the height of the sand is changing. Actually, I guess we should say is increasing by 0.018 meters per second. Okay, just to practice writing those sentences. Okay? All right, example 2. Sand is being poured at a rate of 3 inches cubed per second. So that again is going to be our dV dt. Onto a conical pile of sand that is initially 2 inches in height with a base diameter of 10. So I know initially 2 inches in height with a base diameter of 10 inches. How fast is the radius of the pile increasing? So now it's asking us about radius. How fast is the radius of the pile increasing? So that means I want to find dr dt. At the moment, when the pile of sand is 10 inches in radius. So I know that the moment that I'm looking for, r is going to be equal to 10. Okay, so let's plug in what we know. I know that r over h is always, actually let me organize a little better. I know that r over h is always going to be the same. So my radius here is 5. So that's going to be 5 over 2. Okay, now this one, I want it to be in terms of, I need to solve for h because I need to plug in for h so that everything's in terms of r. So when I cross multiply, that's going to give me 5h equals 2r. So h is going to be 2r over 5. So volume is 1/3 pi 2r, pi r squared times 2r over 5, right? Which I'm actually going to multiply my little fractions, this, and that's going to give me 2 over 15 pi r to the 3rd. Okay, so now we can go and take our derivative. So dv dt, when I multiply this over, that's going to give me 6 over 15 pi r squared dr dt. Okay, now I can go and plug in everything that I know. So I know this is going to be 3. 6 over 15 pi. I know that the moment we're talking about, my r is 10. dr dt. Okay, I'm going to have to go up here and finish this. So 10 squared is going to be 100. 100 times 6 is going to be 600. And then 600 divided by 15 is going to give me 40. So that's going to give me 40 pi dr dt. So dr dt is going to equal 3 over 40 pi, and that is going to be inches per second, or I can simplify that. 3 divided by parenthesis 40 pi is going to be 0.024 inches per second. So my sentence is going to say, when the radius is 10 inches the radius of the sand is increasing by 0.024 inches per second. Okay, so what you guys are going to do now is there's 2 examples for you guys to do on your own. Submit them with accuracy to get full credit. If you need help with them, please feel free to come in for small learning group time. But hopefully after watching this video, it'll make it pretty clear to you.